The magnet on your refrigerator holds up a shopping list. The magnet inside a Tesla motor generates enough torque to accelerate 2 tons of car in under 3 seconds. Both are permanent magnets, but they are made by completely different processes, and the gap between them is one of the most important manufacturing stories of the 21st century. In 2025, the world produces over 200,000 tons of permanent magnets every year. Without them, every electric vehicle stops, every wind turbine stops, every MRI machine goes dark. The hard drive in every computer stops spinning. Permanent magnets are the invisible infrastructure of modern civilization, and almost nobody knows how they are made. To understand how magnets are made, you first need to understand what a magnet actually is. Every magnetic material contains tiny regions called domains, microscopic zones where atoms align their magnetic fields in the same direction. In an unmagnetized piece of iron, these domains point randomly in every direction. They cancel each other out. There are 2 completely different types of permanent magnets in everyday life. Ferrite magnets, also called ceramic magnets, are made from iron oxide mixed with barium or strontium. They are cheap, rust-proof, and adequate for low-demand applications. Neodymium magnets are made from rare earth metals and are in a completely different league. Neodymium magnets require 3 main ingredients: neodymium, a rare earth metal found primarily in China's Inner Mongolia; iron, the most common metal on Earth; and boron, a metalloid that locks the crystal lattice into its powerful magnetic configuration. Together they form NdFeB, the strongest permanent magnet known to science. The word rare in rare earth is misleading. Neodymium is actually more abundant in the Earth's crust than gold by a factor of 1,000. The challenge is concentration. It is almost never found in dense, mineable deposits. And even when mined, separating and refining it requires an enormously complex and environmentally demanding process. The manufacturing process begins in a vacuum induction furnace at approximately 1,300 degrees Celsius. The neodymium, iron, and boron are loaded in precise proportions and melted together for over 4 hours in a completely oxygen-free environment. Any oxygen contamination at this stage ruins the entire batch. The result is a liquid alloy rapidly cooled into thin ribbons. The thin alloy ribbons are then broken down in a process called hydrogen decrepitation. The alloy is exposed to hydrogen gas under pressure. The hydrogen infiltrates the crystal structure and causes the alloy to crack and crumble along its natural grain boundaries, like peeling apart the layers of a croissant, producing coarse powder ready for further grinding. The coarse powder then enters the most critical size reduction step, jet milling. The powder is accelerated to high velocity in nitrogen gas, and particles collide with each other at extreme speed, grinding each other down to a target particle size of just 3 to 4 microns. That is roughly 1/30th the width of a human hair. Throughout the entire powder handling process, the material must never be exposed to air. Neodymium powder is pyrophoric. It can spontaneously ignite when exposed to oxygen. Every container, every pipe, every piece of equipment is filled with nitrogen gas. The powder moves through the factory in a completely sealed, inert environment at all times. This is the step where the magnet is actually born, though it does not look like one yet. The fine powder is placed into a mold and subjected to a powerful external magnetic field. This field forces every microscopic particle to rotate and align its magnetic axis in exactly the same direction. Then the mold is pressed. The press block at this stage, called a green body, is fragile and powdery. It holds its shape but would crumble under moderate pressure. The particles are aligned but not bonded. The magnetic field that created the alignment is switched off, and the block is carefully transported to the sintering furnace where it will be transformed. Sintering is where chemistry takes over from physics. The green bodies are loaded into a vacuum furnace and heated to between 1,000 and 1,100 degrees Celsius, just below the melting point of the alloy. At this temperature, the particles begin to fuse together at their surfaces. Over several hours, the porous green body densifies into a solid metallic block. After sintering, the magnet undergoes 2 stages of tempering, precise heat treatments at lower temperatures. The first stage at around 900 degrees Celsius for 3 hours. The second at around 500 degrees Celsius for 4 hours. Each stage adjusts the microstructure at the atomic level, maximizing coercivity, the magnet's resistance to losing its field. The sintered and tempered block is still not a magnet. To create the permanent magnetic field, the block is subjected to a brief but extremely powerful pulse of electricity through a magnetizing coil, a field far stronger than the magnet's own final strength. In an instant, the domains lock permanently into alignment. The magnet is born. After magnetizing, the magnet is machined to its final dimensions using diamond-coated grinding equipment with water cooling, necessary because NdFeB is extremely brittle. Then it is plated with a nickel-copper-nickel coating to protect it from corrosion. Without this coating, neodymium would rust and lose its properties within weeks. Before looking at where these magnets go, a critical safety point. Large neodymium magnets are genuinely dangerous. 2 magnets the size of a book, placed 30 centimeters apart, will snap together with enough force to crush fingers. They shatter on impact like glass, sending sharp metal fragments. Only trained personnel handle magnets above a few kilograms. In an electric vehicle motor, stacks of neodymium magnets generate the rotating field that drives the rotor. In an MRI machine, they create the field that images soft tissue. In a smartphone, a neodymium magnet 3 millimeters wide makes the device vibrate. One material, 3 completely different scales of application. China currently produces approximately 90% of the world's rare earth elements and processes an even higher share into finished magnets. This concentration creates a strategic vulnerability for every nation building electric vehicles and wind turbines. The magnet supply chain has become one of the most geopolitically contested industrial dependencies of the 21st century. From a fridge magnet to a Tesla motor, from Inner Mongolia to your phone in your pocket, the permanent magnet is the hidden engine of the modern world. If this video changed how you see magnets, please subscribe, hit like, and share it. We publish every week.